Introduce briefly myself. My name is Vicente González. As you mentioned, I'm currently the CTO at FOSSA Systems. It's a really big pleasure to be here with you, sharing our latest updates regarding FOSSA Constellation and FOSSA Sat platform. So I would begin with a brief introduction, just in case we have any attendee that is non-related with space business or with NewSpace business. Then we discuss a bit about the differences between CubeSat and PocketQubes. Then we will have a look at FOSSA 2 Evolve platform, and then we will design a constellation using this kind of PocketQubes. So let's begin with a brief definition of what implies old space and new space. Old space is mainly characterized by high cost. There are expensive long-term missions, usually supported by space agencies, that consume a lot of human resources. Normally, the teams are compounded by hundreds of people. They usually take a long development time, and the operation can last for years. For example, Gaia, which is a mission with more than 6 years old. And even though the state-of-the-art technology that is usually related to old space, once launched, could be obsolete, like, for example, a satellite Ingenio. And on the other hand, we have NewSpace, which, as far as I understand, is mainly based on private initiatives, developing smaller spacecraft based on COTS components and standardization and miniaturization of the technologies, leading to fast development time and fast constellation deployment. Just I don't know if any of you has ever made the estimation, but in this side of the picture we can see the NBSat, and here we can see several CubeSats and even a PocketQube. And almost 1.4 million of 1P PocketQubes would fit in the volume occupied by the NBSat in launch configuration. So basically, NewSpace can be understood as the solution of the so expensive barriers to entrance to the space business. We will focus in this presentation on this part of the diagram. On the top of the image, we can see the classification of the spacecraft regarding the mass, and on the here we can see the classification regarding the form factor. You know that we can see here CubeSats and PocketQubes. We will focus on Picosatellites, which are satellites with spacecraft mass below 1 kilogram, and we will discuss about 0.25 U and PocketQubes. So let's start with a brief of history of CubeSats and PocketQubes. In 1999, the first CubeSat standard was created, developed by Professor Puig and Professor Twix. 4 years later, in 2003, the first CubeSat was launched, and 10 years later, the commercial CubeSat launches overtook academic and scientific launches, meaning that several companies are making business out of this kind of satellites. Later this year, in November 2013, the first PocketQubes were launched, when CubeScout, Bigger One, etc. Then in May 2018, the first CubeSats that left Earth orbit were launched. If I don't remember badly, there are the Marco CubeSats within an interplanetary program of NASA. Then in that year, later in June, the first PocketQube standard was created by Alba Orbital, GAUSS, and people from the Technical University of Delft. And then 1 year ago, in December of 2019, the second successful launch of PocketQubes was accomplished. FOSSA Sat 1 was launched, as Julian mentioned during his presentation earlier today. And now we have, but by the end of 2020, the Picosatellites mission within the maiden flight of Farfly Aerospace will include 2 PocketQubes developed by FOSSA, FOSSA Sat 1B, which is this PocketQube, and FOSSA Sat 2, which is this PocketQube. And as Julian mentioned, in April 2021, we hope to successfully launch the first PocketQubes FOSSA 2E that would become part of our own constellation. Now let's move on to a brief comparative between CubeSats and PocketQubes. On this side of the screen, you can see how the different parameters are related. Regarding the volume, this relation is not completely true because since in CubeSats, the volume is usually constrained by the deployer. In the case of PocketQubes, we have some margin, and that leads that if we have a CubeSat with a backplane and with deployable solar panels, at the end, the relation between the number of PocketQubes that could fit in the volume of a one CubeSat is instead of 8, it downs to 4 or 5 PocketQubes. Now we can see in this part of the image, we can see a small comparative between some of the parameters in which PocketQubes are kind of better, and other CubeSats are stronger. On the one hand, CubeSat have more flight heritage. There is more codes availability for CubeSat. They usually have higher capabilities than PocketQubes, but on the other hand, usually to develop a CubeSat and even launch it is usually much more expensive than in a PocketQube. On the other hand, we have PocketQubes that reduce the cost and time of developing and launching the satellites, although the reduced volume and the reduced power budget leads to limitations regarding the applications that are usually limited to IoT connectivity services, small Earth observation platforms, data relay, etc. We will focus, as you can see, well, this is an overview of the type of satellites launch. As you can see, the 3 CubeSats represents the majority of the satellites launched and expected to launch. This is due to the constellation of Planet and Spire, which are based on this form factor. But we will focus on the 0.25U CubeSat and the PocketQube. As you can see, the numbers are quite similar, with 61 CubeSats expected to launch or already launched up to date, and 60 PocketQubes up to date. So you can see here an example of a 0.25 CubeSat, which is the Space B developed by Swarm Technologies. And here you can see the FOSSA 2 Lite platform that would be launching within the PicoWest mission. In this image, we have tried to compare different aspects of the satellites to see if there is an optimum solution for this kind of applications. On the one hand, regarding the power, this kind of satellites can generate up to 2 watts. Let's consider that each solar cell generates 1 watt. FOSSA 2 Lite just can generate up to 1 watt. But on the other hand, we have FOSSA 2 Evolve, which is an evolution of this design that will carry on deployable solar panels that would let us generate up to 9 watts. Following with the comparison, we have the attitude determination and control system, in which the swarm space bees are mainly based on magnet torquers, same as FOSSA 2 Lite. And on the other hand, we have the FOSSA 2 Evolve platform that would carry magnet torquers and reaction wheels. Magnet torquers would be used in order to desaturate the reaction wheels. And we are working on 2 different possibilities, one with 3 reaction wheels and one with 4 reaction wheels in a pyramidal distribution. Another key aspect that we consider while doing this kind of mission is the possibility of hosting extra payload space. We assume that the 0.25U CubeSats don't have enough space to have another extra payload. In the case of FOSSA 2 Lite platform, this space is below 0.5 Ps, and in the case of FOSSA 2 Evolve, the extra payload space is around 1 P and 250 grams. And finally, regarding the launching cost, in this case, launching CubeSats or this kind of CubeSats would be cheaper than launching PocketQubes. Uh, Another advantage of this kind of CubeSat is that it can fit to fill in gaps in deployers. For example, imagine that one university has developed a 1.5U, then you could fill the gap with this kind of CubeSats. And on the other hand, we have with the current launch opportunities that launching these 2P PocketQubes would be at around 35,000 euros. So as you have seen before, it seems that FOSSA 2 Evolve platform is such a good solution to optimize the power generation, the control, and, and the extra payload space. As Julian mentioned, we are really encouraged to you to see in more detail the technical data sheet that is published in the website of the workshop. As I mentioned, the power generation is up to 9 watts with the solar panels deployed. The attitude determination and control system is active control with 3 reaction wheels and the magnetorquers in order to desaturate the wheels. The downlink data speed is up to 0.25 megabits per second in UHF. We have, as I mentioned, the payload volume up to 1P with 250 grams, regulated boost, 3.3 watts, maximum power peak tracker, 4.5 watts power for storage, solar panels, and 512 megabytes on board memory. And our objective with this platform is not just to let people to prove their technology or their payload, but also to provide our own services with IoT. So now let's have a look of constellation based on this kind of platform. The key objective, as you can see, is to maximize the coverage, minimizing deployment time and cost, which is intrinsically related to NewSpace paradigm. The study case, as I mentioned, is low power and low latency application, which lead us to perform IoT services in narrow band. And here in this graph, you can see the different launch opportunities. As you can see, we will focus on these 4 type of orbits, which are synchronous between 500 kilometers and 550 kilometers. PocketQubes launched from the International Space Station at 400 kilometers, and PocketQubes deployed from Cygnus spacecraft at 500 kilometers. If we put this kind of orbits in our funnel, then we have our final goal, which is the constellation. In order to deploy the constellation, we will make use of our Pocket Pod. As Julian mentioned, there are still lags in the launch opportunities regarding PocketQube, so we assume that Pocket Pod is a really good option to launch your PocketQube. It has an 8P capacity. For example, in this case, we could launch 4 FOSSA 2 per pods. The objective is to launch multiple Pocket Pods per launch. This is the Vigoride platform developed by Momentus with all these deployers inside. And the cost will be reduced up to 18,000 euros per 1P. As Julian mentioned, Pocket Pod can be integrated vertically and horizontally. And now that we have the tools to deploy our constellation, we have to focus on which kind of constellation we have with the current opportunities. This is an example of a constellation composed by 48 satellites divided into 4 planes and with 12 satellites per plane, which is similar to launching 3 full Pocket Pods per launch. I don't know if you can see, but for example, this constellation is formed by 3 asynchronous orbits, one dusk dawn, one high noon, and one, let's say, Earth observation with an LTAN of at 1030. And this is the expected satellite distribution after performing the maneuvers of differential drag. The 12 satellites would be optimally separated around 30 degrees each. So we know how we won the constellation, but let's now discuss how are we going to reach the optimal distribution of the satellites. And the key lies on the attitude determination and control system. We will use the reaction wheels to change the relative position and the attitude of the spacecraft. We will have the minimum drag configuration and the maximum drag configuration with the solar panels deployed. And by changing the ballistic coefficient, we would be able to separate along the orbit the different satellites. In this plot, you can see the orbital lifetime. It's a parametric simulation considering different ballistic coefficients. Let's forget about these cases because too optimistic. It means that they are flying always with a minimum drag configuration. But as you can see here, the lifetime of our satellites would be between 1 year and 3 years, more or less. That will lead us to be following the technological developments in order to be continuously launching satellites, and each time the satellites would be technologically better. Finally, this is one of the figures of merits of the constellation. It's related to the revisit time. With this kind of constellation, where you can see some gaps, we arrive to this revisit time. This graph means that the 50% of the times the revisit time would be below 5 minutes. The 90% of the times the revisit time would be below 8 minutes. And the worst case scenario would be one case in which the revisit time would be one orbit, would be around 95, 97 minutes. So that's it. Don't forget that PocketQubes recover the initial spirit of CubeSats. FOSSA it's an inexpensive, reliable, and flexible solution for IoT services. The Pocket Pod lead us to decrease a lot the launch cost, and we are aiming for a constellation to be anywhere, anytime. Thank you so much for your attention. Do not hesitate to contact either Julian or me if you have any questions. Thank you very much.